Hopefully you just watched the cylindrical shell kind of introduction video, but we are moving into 7.3 today, and we're going to be in here in this lesson of the book the entire week, and we are going to look at an alternative method for finding volume of solids of revolution. So we're still looking at these three-dimensional solids and trying to figure out kind of how much they would hold if they were hollowed out. And this alternative method that we are going to focus on this week is called the shell method or cylindrical shell method. Okay, now today is all about me just introducing you to it and how you're going to apply it to a problem. So don't yet get caught up on when am I going to know if I should use the shell method or the disc method. That was what we did last week. We will focus on that in lessons to come. Okay, so the notes say we will first learn to apply the shell method to find the volume of a solid. That is today. And then over the next few lessons, then we are going to compare the disc washer method. That was 7.2. And we're going to compare it to the shell method, which is 7.3. There are some times that you have to use a certain method. The other method fails. Okay, so there's your incentive right away to learn the shell method. Some of these, yes, you can use the disc and washer method, but again, I'm going to emphasize that there are some problems that you cannot use disc and washer. So that's why we have to learn a new approach. So after watching the quick introduction video, some of this will sound familiar, but let's go over kind of the key ideas or concepts of the shell method. So what we're going to start with is we are going to start with a function, a two-dimensional representation of space. So they might say we want to go ahead and take this space that is bound by the function f of x and rotate it about the y-axis. Okay, so the first thing that you notice is we are taking a function written in terms of x. So the function is in terms of x, meaning y equals, and we are though looking to rotate it around the y-axis. So the first key idea is in this rotation, our representative rectangles are going to be parallel to the axis of revolution. So if I go ahead and draw one of those in, that is our key difference when we compare it to the disc washer method. Okay, in this case, our representative rectangles are parallel to the axis of revolution. In our case, it is the y-axis. So what we do in the shell method is we think about our rectangle rotating 360 degrees about the axis of revolution. Okay, and what we would end up getting if we rotated our entire yellow area is this solid that you see here, okay, but we need to think about what it's composed of. So if I draw in my rectangle again, and I think about rotating it, I'm going to mirror image my rectangle, okay, I see that a cylinder is going to form. Okay, so there is my cylinder, and the height of the cylinder was defined by the function. Okay, now if I draw in another cylinder by using a representative rectangle that is closer to the y-axis, okay, you can see the cylinder is going to be inside of my other cylinder, and then I could make another cylinder that maybe uses the edges of the function. And if I go ahead and rotate that, okay, that is going to be kind of even shorter. So we have cylinders inside of cylinders inside of cylinders. And I don't know if you've seen around Christmas time the Santa Clauses that fit inside of each other. That's what I think of when I think about the shell method. Okay, so the key ideas is that those three cylinders that I just drew, okay, the height of the cylinder is defined by the function value, okay, that is written in terms of the opposite axis that you're revolving around. So remember, we were revolving around the y-axis, but our function is written in terms of x, so it'll be y equals. Okay, but then also, what controls the volume of each cylinder that we drew? We know that we have to consider the radius of each cylinder in order to find the volume of each separate shell. Now, the radius of these cylinders is simply x. Okay, if you look at each cylinder, I started at the origin, and for the red cylinder, okay, x is small because it's close to the origin, and for the green cylinder, x is going to be larger, but it's just simply defined by the distance from the axis. So, if we combine this all together and we think about let's find the volume, we need to add up the volume of these individual shells, these individual cylinders that we drew, okay? So first we need to remind ourselves of the volume of a cylinder. Okay, so the volume of a cylinder is going to be composed of a few different parts. Okay, well, we need to think about, okay, slicing the cylinder and considering the length, the width, and the height. Okay, so the length that we heard in the video is the circumference of the circle, the circular part of the cylinder. So 2 pi r is what we are considering the length of our cylinder. Okay, and then we have to multiply that by the height of the cylinder. So I'll say h. Yes, that is considered the height, but what was that really controlled by? That was controlled by the function that we were given, because the height of each cylinder changes because the function is curved. And then we have the width, which we are going to call delta x, because you can see when I drew in my representative rectangles, they had a little bit of width. Okay, so this in the intro video is referred to as the thickness. But we know that in calculus, the goal is to approach infinity. So we are thinking about dividing this solid into infinitely many shells. So if we're going to divide into infinitely many shells, then we know that our thickness, our delta x, has to approach 0. When that is the case, when our delta x approaches 0, we can then move into using integration. Okay, and that is the same idea of that disc and washer method, okay, but now we're slicing the solid into something different. But we studied cylinders a lot in geometry, okay? So here is the key kind of idea and formula as to how we are going to find the volume using the shell method. Okay, so you've got to sort through. Disc method was related to area of a circle, pi r squared. But shell method is related to surface area of a cylinder. Okay, so I'm going to start in my second column over here. And let's look at when we are asked to revolve a solid about the y-axis. Okay, so if we're taking our solid and rotating it about the y-axis, in this case, okay, this is what we're going to do. We're going to relate it to 2 pi r times height, okay, but our 2 pi is a constant, so this will always be a constant. And then, okay, we are going to take P of x, they use the letter P to represent the radius of the cylinder. Okay, so this P of x, we are going to call it the shell radius. And usually if we're rotating about the y-axis, not a line that's off of the y-axis, it's just going to be x. Okay, because it's going to be the distance from the axis. So if this is indeed the y-axis right here, what would this distance be? It would just be x. Okay, and then h of x is used to talk about the height of the cylinder. 2 pi r times height. That is the equation or the formula for surface area of a cylinder. So this is the height of the cylinder, but it's going to be defined by the function written in terms of x. Again, your rectangles are parallel in this case to the axis of revolution. Okay, so that's the key difference. So then when we go into looking at revolving around the x-axis, okay, we see immediately, if this is our axis, we're rotating around the x-axis, we are going to have our integral written in terms of y, because our rectangle is going to be parallel to the x-axis. So we know that if we're looking at horizontal rectangles, we have to have functions written in terms of y. So once again, okay, this stands for the shell radius, and the shell radius, if you're going from the x-axis, if I think about this distance right here, that distance is simply y. So most of the time it's going to be y until we start rotating around lines such as y equals 2, y equals 3, kind of like we did during 7.2. And then the height is going to be still defined by the function, but the function has to be written in terms of y, so it has to be an x equals form. So a lot of times you will see people write f of y, okay? So everything, this dy reminds you, everything has to be written in terms of y. Okay, now here, again, we can see I skipped this on the first example in our table, so we'll go back in a second, but the limits of integration do not come from the axis of revolution. They come from the opposite. So again, if we are using dy, the c and d have to come from the y-axis. Okay, so the limits of integration come from the y-axis because we have to think about the different shells are coming until we hit D. Okay, so then when we look back at rotating about the y-axis, our limits of integration have to come from anything to do with x because we're integrating in terms of x. So again, the heights of our shells go from A to B, but we are rotating them. I'm going to erase this. Okay, like so. All right, so we are going to apply this to two problems. Your homework tonight is going to be basic problems, and then we're going to continue on with some more complicated in the next few lessons. So example 1 says to find the volume of a solid of revolution formed by revolving the region that is bound by the function x minus x cubed and the x-axis, so the region that we're focusing on, okay, don't ignore the axes that they give you. We are rotating this region about the y-axis. So think right now, if you were to try to use the disc washer method and you drew in those perpendicular rectangles, how are you going to define the height of this line when you only have one function? The top and the bottom, big R and little r, are defined by the same thing. So that's going to be very, very difficult. Okay, so I'm already kind of jumping ahead to when you need to use which method. So we are going to keep this function written in terms of x, and we are going to draw a representative rectangle that is parallel to our axis of revolution. And we're going to kind of picture, okay, if we draw in the mirror image and I redraw that representative rectangle, we're going to picture a cylinder that is formed when you rotate this rectangle. And then we can picture another cylinder that is formed by a rectangle, maybe with a lower height that comes later on. Okay, and so on and so forth. So we have cylinders within cylinders within cylinders. So if we're going to find the volume of this three-dimensional solid, okay, then we're going to follow the guidelines of 2 pi r times height. So that's how I kind of really remember what I need. So 2 pi is a constant, And the radius of the cylinder, so if I go to my purple rectangle, what is the length of that black line? The length of that black line is x. It's just simply measured from 0 out to where I want it to be. So my radius is going to be x. That changes because you can see that the green radius is further than the purple. So the radius is not constant. Okay, and then what is the height of each rectangle defined by? This function right here. But again, we have to keep it written in terms of x, because that would give our height of each thing that I've drawn there. So x minus x cubed. Now we don't square this, okay? That's a common mistake because we do square with disk and washer, but there's nothing about squaring here. Dx. Now, what am I looking at in terms of my limits of integration? My cylinder starts at the axis of revolution, and I have to draw in my representative rectangles for all of these radii until I get to 1. So 0 to 1, okay? Now I integrate. I know you can do this on your calculator, but I feel like as a teacher, we need to use our mind a little bit, okay? So this one works out nicely. We have x squared minus x to the 4th, so when we integrate, we get 1/3 x cubed minus 1/5 x to the 5th. I love when they give me a 0 and a 1. Okay, so I have 2 pi times, I'm just going to plug in the 1/3 minus 1/5, and I know 0 is just going to result in nothing. So when I do 1/3 minus 1/5, I get 2/15. So 2 pi times 2/15 is going to be 4 pi over 15. Okay, and that is going to be units cubed. That gives you the approximate value of 0.84. It is fine for you to give me approximations still in this section, but I just wanted to review some integration. The final example of this first lesson, okay, is we are asked to find the volume of a solid of revolution that is formed by taking this graph. It's written in terms of x, so that's kind of maybe hinting that we're going to be looking off the y-axis. The y, so we want to bound by x equals e to the negative y squared, and the y-axis from 0 to 1. So this is important. So from 0 to 1, so if I shade in the region that we are rotating this entire yellow region here, and they want to rotate about the x-axis. Okay, so if we would do our perpendicular rectangles from 7-2, okay, these perpendicular rectangles would utilize a different function than these perpendicular rectangles. So this would be a 2-part integral if you wanted to take that route. But if I look and see, I don't want to solve this in terms of y anyways. If I used those vertical rectangles, I would have to solve it for y. No, thank you. So I am going to go ahead and use rectangles that are parallel to my axis of revolution and think about what this would end up looking like. Okay. So I have my mirror image and then I draw in my cylinder. So here's just one cylinder. Okay, and I'm going to go ahead and consider the dimensions of this cylinder. I need to know the radius, and I need to know the height. Okay, so when I use my formula, 2 pi integral, what is this radius controlled by? It's just y. It's the value of y. Wherever you're at on the y-axis is going to give you the radius of that particular cylinder. And then the height of my cylinder is controlled by the function, and luckily it's already solved for x. It's written in terms of y. If I've already written a y here, and I try to have an x somewhere else in my integral, I know I am wrong. Everything has to be written in terms of y when you're rotating around a horizontal axis using cylindrical shells. Okay, now again, you can use your calculator on this, but not yet. We need to figure out, okay, where our cylinder is going to start, where are they going to stop? Well, I could draw a cylinder out here, right? And I could rotate it all the way. So where do I draw my last cylinder? Right here. So remember, your limits of integration come from the opposite axis than your revolution for cylindrical shells. So at this point, we can go ahead and see, E. When we take the derivative of E, what's the derivative of E to the X? It's E to the X. So again, yes, you can use your calculator, but a little review. If my U is negative y squared, my du is negative 2y. Well, I have my y here, I have my 2 here, but I don't have a negative anywhere. So if I go ahead and move my negative over, I have negative du, sorry, there should be a dx here. Negative du equals 2y, not dx, what am I thinking? dy. Okay, so now I do have my, let's see, my 2y dy. So now I can think about the integral. Okay, I need to put in a negative though because that needs to take place when I substitute du. So I'm going to pull that out front and I'm going to think about e to the u du. This is a great review. What's the integral of e to the u? It's just e to the u. So negative pi e to the u, I'm leaving my limits off for a second. Okay, but when I make my u substitution back, I have negative pi e to the negative y squared. You can certainly go ahead and try to take the derivative of this using chain rule, and guess what? You're going to get back to this original function right here. So then I'm going to integrate this from 0 to 1, and you need to be careful because when you do plug in 0, it's not 0. So I'm going to think about negative pi times, okay, take that constant out front, e to the negative 1 squared is negative 1, minus e to the negative 0 squared is 0. And when you go ahead and use your calculator to evaluate that, okay, there's no way around anything but an approximate answer. When you multiply by negative pi, you are going to get 1.99 units cubed, okay? Don't stress about all of the integrating. Like I said, if you plug this into your calculator with the proper limits, you will get this answer out, okay? So, focus on this new formula that we have to use with our y-axis revolution and our x-axis revolution. See how it goes, and then we are going to continue on in the next video focusing on kind of when we use which method and some curveballs that might be thrown at us. Keep up the hard work. Miss you guys, and we'll talk later.